Hello everyone, my name is Juan. Today I'm going to talk about Fresco, a scalable interaction framework for skill and query processing on clouds. Cloud computing has increasingly raised its tensions over the last year, and many organizations try to adopt cloud computing technology to benefit from resource and cost elasticity. Despite huge benefits, cloud computing encounters security threats, and these threats may come from the distributed architecture of cloud computing or insider threats. Over the last year, encryption has become one of the powerful techniques to protect confidential data stored in untrusted environments like clouds. And with this approach, sensitive data is first encrypted at a trusted components like connector before the corresponding ciphertext is sent to cloud for management. In this paper, we consider the system having the following properties. First, we would like to support non-address range queries because it replaces important operation in database. The second, the system has to support high interaction throughput and has a strong privacy protection. There are many work have been done on the topics of range query processing on encrypted data. However, none of existing schemes can cope with fast incoming data. So in this study, we developed our solution based on PinIQ family because the solution outperformed the others in terms of security as well as performance. So to adapt PinIQ to the context of fast data, in this paper, we propose a new system design of a privacy-preserving query system, especially for high-throughput data. Our system can achieve good performances in terms of throughput and the publishing time. Before going to the description of Fresco, I would like to briefly describe PinIQ, especially how to build clear skill index in PinIQ. Given a dataset of trusted components, PinIQ first build a clear index over this dataset. In this clear index, each node has two components. The first one is the range interval, and the second is the count. The count indicates the number of the records that belong to that interval. And PinIQ also maintains the pointer between the leaf nodes and the records in the dataset. To make this index private, PinIQ proposed to add blah blah noise to the count of the index to get the better index. However, the noise may be positive or negative. So that leads to a situation where the count of the leaf nodes is different from the number of the pointer that leaf holds. To address that inconsistency, PinIQ proposed to add some dummy records into the dataset when a leaf receives a positive noise. On the other hand, when a leaf receives a negative noise, PinIQ moves the records, the real records, to the overlay arrays. Finally, PinIQ encrypts the datasets and overlay arrays, and then send these data structure to cloud for serving range queries. Although PinIQ can provide very fast range query processing, it incurs bottlenecks in the system in case of high rates of incoming data because it has to publish data in large batch. To address the limitation of PinIQ in Fresco, we try to process incoming data on the fly instead of publishing data in large batch. We design Fresco based on the channel thing architectures, so that makes Fresco more scalable. In Fresco, we consider three types of first rate offline attackers who can get copies of the encrypted datasets and the skill indexes. Simple online attackers who can record or observe on information available on clouds. The last one is the informed online attackers who can know the time distribution of real datasets. For this type of attackers, one challenge of Fresco is how to privately release dummy records and remove real records from the PinIQ index. Because When a dummy records arise at cloud at an unlikely time, that records can be recognized by this first rate. To achieve high interaction throughput in Fresco, we propose a new architecture in which we try to parallelize on heavy operations such as parsing and encrypting of data. Instead of using the whole index for checking and updating operation, we use the arrays of interval for keeping the noise and the counts of the index. So that's help to reduce the complexity of the operation from bit O log kn to bit O1, where k is a branching factor and n is the index domain. We found that asynchronous publishing methods can lead to a bottleneck in the system. So for that reason, we designed an asynchronous publishing mechanism. To do that, we add a new component mergers in our architecture. This component is responsible for publishing tasks only and runs independently of the other components in this architecture. With this approach, the publishing time in these architectures is reduced significantly and the throughput also increases. To protect the interactive noise against online attackers, we propose randomer. It's used to perturb real-time distribution. So how it works? This component maintains a fixed size buffer and at first on crew and dummy records will be mixed together in this buffer. When buffer is full, randomer will randomly pick one record and release it to the next component. So for that reason, when an encrypted record arrives at cloud, this first read cannot distinguish between the real or dummy records. We also prove that Fresco satisfies a computational variance of differential privacy against offline attackers and simple online attackers, while mitigating information clicks against the informed online attackers. To validate our solution, we use two real-world datasets, NASA and Goala, and we can see the three main metrics: interaction throughput and the publishing time. The publishing time is the time required to publish a dataset. The last one is throughput duration. We also compare Fresco to PinIQ++ and parallel PinIQ++ because these solutions have been developed to deal with the context of high rates of incoming data. Regarding the interaction throughput, we use different size of a cluster. And when we increase the number of computing nodes in the cluster, the throughput also increases. Especially when we use 12 computing node cluster, the improvement is about 43 times and 5.6 times as compared to PinIQ++ and parallel PinIQ++ respectively. Considering throughput duration, as we can see in the figure, Fresco experiences the lowest duration between the three prototypes and under 18% in two datasets. For publishing time, we measure the time to publish a dataset as on components in Fresco. And we also use different size of cluster and different size of datasets. The result is that the time to publish a dataset is less than 1 second as on components. To conclude this paper, in this paper, we propose a novel design of a privacy-preserving query system. In this system, we propose a distributed architecture, a new data representation, and an asynchronous publishing mechanism. And our system can ingest about 165,000 records per second. It also has a strong privacy protection. In the future, we will investigate the situation where an individual has multiple records. And we also interested in investigating alternative indexes such as mastery and ART. Thank you very much for your listening. And here, some references you might talk today.